Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we are going to move from single phase to three phase power supply. The why we go for it, the fundamental reasons why we need three phase power supply. So, to quickly recap, suppose I had only a phase and it was giving me a, let us say I took the voltage as the reference and the current which it was drawing for all sinusoids at 50 hertz was lagging by, so this is my V phasor, this is my I phasor, and it is lagging by an angle of 5 degrees. Inductive load, basically a kind of a inductive load, not pure inductive, but inductive. So, then PA of t, instantaneous power, this is important, that the instantaneous power will be Vm Im sin of omega t into sin of omega t minus of phi, which can be written as Vm Im by 2 into 2 sin of omega t sin of omega t minus phi, but 2 sin A sin B is cos of A minus B. This is my A and this is my B. So, 2 sin A sin B is cos of A minus B minus of cos of A plus B, which can be written therefore as cos of A minus B will be cos of phi minus cos of A plus B will be 2 omega t minus phi. Now, we took the average power of this. If you recall, we said this is 1 by time period PA of t, because why did we look at the average power? We looked at average power because the instantaneous power is pulsating, because the instantaneous power is pulsating with second harmonic. The double frequency oscillation of 2 omega t is superimposed over this Vm Im cos of phi. So, therefore, we said we have to look at the instantaneous value, and we did discuss that the average value of any fundamental frequency or harmonic frequency sine or cosine over a cycle will be 0. So, therefore, the average value is just going to be equal to this particular value, and so we derived last time that this is Vm Im cos phi by 2, which I wrote as Vm by root 2, and I said that this is the RMS value which I will connect in the next class. And so, this P average, so usually we do not show P average, we just show it by capital P usually, is so many watts. So, if this is the average power per cycle, what I told you last time was that you could think of this as two phasors now not having peak as their length, but rather RMS value as their length, and I project them, I project this current phasor onto the voltage phasor. So, it is like saying that if this is my current, this is my voltage phasor, the sine of omega of t, and let me sketch lightly this as my current phasor. So, this is V, this is I, it goes like this, and this angle, if I take this as, if I take the x axis as omega of t, then I can directly mark angles. Then this angle here between the two appropriate zero crossings, is called as the phase angle phi between the V and the I phasor. This is peak is Vm, and this peak here is Im. Now, this Im, this phasor here, I want to write this I sine of omega t minus phi. If you expand it, I mean geometrically I have shown you this, you can think of it as projection, but I want to connect it trigonometrically, I mean in the time domain also, not just on this way. So, then I write sine a minus sine of a minus b as sine a cos b minus cos a sin b, minus cos a sin b. So, in other words, I can write this as I m cos of phi sin of omega t minus I m sin of phi cos of omega t. So, now the component, now observe very clearly, here I said that when I project it onto the voltage phasor. So, this phasor comes in, the component which comes in phase is I cos phi, and the component which comes in quadrature is I sin of phi. That is what I had said. Now, observe carefully here. What I am saying is my reference is, so let us, what is this is my I a of t, now expanded like this. Now, what is V of t? V a of t, I had taken it as V m sin of omega t. So, now suppose if I look at P of t or P a of t, which is V a of t into I a of t, then I have to multiply this with this term, and then this term also has to be multiplied with this term. So, we are doing the same thing in many different ways, but the important thing is that we should remember it, really we should never forget what we are doing. I mean many different ways, when we look at the same thing, it becomes pakka, so to say. And what we want to make sure is the basics we get it very clearly. What are the drawbacks of single phase power, what are the drawbacks of, what are the advantages of 3-phase power, what are the disadvantages of 3-phase unbalance, what are the advantages of 3-phase balance. These fundamental things, you should know very clearly. Even if somebody wakes you in the night and asks you, why are you using a 3-phase supply, why not just use a single phase supply? As an electrical engineer, you should be able to immediately give correct answer. You should not be found groping like a lyrics of a song. For example, we hear so many songs and we get sometimes confused with their lyrics, but if some song we really like, then we probably know its complete lyrics properly. Similarly, here when you look at these basic concepts from many different ways, you would realize that it's only then that you really appreciate the beauty of it, and you can anytime if a doubt comes in anybody's mind or in your mind, doesn't matter, you can very quickly like an expert work it through and say, okay, this is what it is. So, that is the reason why I am trying to bring out, and in the process it shows you so many beautiful ways of looking at the same thing. So, VA of, so the instantaneous power, when you do this multiplication, is going to be, first multiply this term with this term. So, you will get VMIM cos of phi into sin square of omega t, and then you multiply this term here. So, you are going to get minus of VMIM sin of phi into sin of omega t cos of omega of t. So, now you would, which I will further write it as VMIM by 2, okay, first term let me just keep it as it is for the time being, VMIM cos of phi sin square of omega t minus VMIM by sin phi sin of twice of VMIM by 2 sin phi divided by 2 sin of 2 times of omega t. So, now you can really appreciate, this is in this is in my this is my Vm sin of omega t. In phase with it, you mark my words, in phase with it means every instant of time exactly following in the same way, in phase with it, I have the component whose peak is, current component whose peak is Im cos of phi. So, what is this component? And this is this component, if you notice it, when I multiply them together, it comes with Vm Im cos phi sin square omega t. So, that means its peak value is Vm Im cos of phi, and it is always non-negative. Why? Because when this is positive, this is positive, when this has hit its peak, this has hit its peak, when this has gone to 0, this has gone to 0, when the voltage has gone negative, so has this fellow gone negative, and again therefore, their product is positive, and if you sketch it, it is going to look the component 1, I will just call it as component, in phase component, I will call it as P1 of t. So, this is how it is going to look at its peak being VMIM cos of phi, and this is actually, if you look at it, this is a double frequency waveform, right? I mean, why is it double frequency waveform? Because this is where it completes its cycle and then it starts repeating itself. But this is one time period of fundamental frequency. This is only T by 2. So, therefore, one cycle is completed in T by 2, means it repeats twice one every cycle. So, therefore, it becomes a double frequency waveform, and it is always dissipative. The important thing to note is that this is first component is always dissipative. So, there is the source is supplying the power to the sink and the sink is continuously consuming it. That is what it means, you know, there is nothing going back from sink to the source. So, I have this as my sinusoidal supply Vm sin of omega of t. I have this as a load, maybe RL, kind of a series combination of RL or whatever. This is the Ia of t. In general, this is, if it was in general, this when this goes from, when it is positive, I mean to say when this product is positive, then I am saying, what I am saying is that power is being supplied from source to the sink, and conversely when it becomes negative, this is on the instantaneous power. When the instantaneous power becomes negative, then the power is being returned from source and sink. So, power is now being returned from source to sink. So, this is instantaneous power positive, this is instantaneous power negative. Now, look at your home, for example, you draw power from the three phase supply or single phase supply which comes to your own. Your really intention is not to do this task. This only happens because of the inductive nature of the load or capacitive nature of the load. Usually it is inductive in nature. That means there are some dissipative circuit wise, there are our load is a combination of series parallel kind of connections of the elements R, L and C. The inductive and the capacitive elements are the storage elements. So, even though we want mostly drawing power to do some work, maybe light a bulb, maybe run a refrigerator, maybe a air conditioner, maybe a geyser, maybe a computer, maybe a TV, whatever it is, we actually want this part of it, but inadvertently due to the inductive or capacitive nature of the load, this part also happens, because when a current goes into inductor, you know that half of Li square gets stored in it, or if the if V is a voltage on a capacitor, then the energy which is stored in it is half of CV square. So, these things, if as per these instantaneous values, the stored energy in the inductor or the capacitor will be increasing or decreasing, but a resistor element is always dissipating power. So, suppose this current has reached its peak value, then this energy stored has become maximum. This energy stored has become maximum. So, slightly digressing for time, just let us say this is Im sin of omega t, and this is just connecting this is just moving into a inductor. Actually, you can take it sin of omega t minus phi also, there is no problem. Then half of Li square, the energy stored in the magnetic energy stored in the inductor, will be half of Lm square Im square sin square of omega t minus of phi, and so this will be equivalent to half of Li square. Yeah. So, it will peak, its peak value Emax is going to be half of Lim square and then I will write it by 2, and then 2 sin square omega t I will write it as 1 minus twice of omega t minus of phi. Is it not? What did I do? Basically, I said 2 sin square theta is side. What did I say? I said 1 minus 2 sin square theta is cos of 2 theta. So, sin square theta can be written as half of 1 minus twice of cos of theta. So where the theta is this particular value. So, the two coming out here in common. So, if you look at this, what is it instantaneously? Now, while drawing, I am going to just draw it with for phi equal to 0. Now, this is your Emax by 2. So this line here indicates Emax by 2. This is your value here, starting point, offset value. This is your offset value, and then you are getting a double frequency oscillation. I am taking phi to be equal to 0. So if I take the phi to be equal to 0, it becomes basically 1 minus cos of 2 of omega of t. So at t equal to 0, its value is going to be equal to net value t equal to 0. If you put 1 minus cos of t equal to 0, 1 minus cos of 2 omega t is going to be 0. The cos of 2 omega t is 1, and it comes with a negative peak. So, what is happening is you are superposing this is I am now drawing minus of 2 of cos of omega t. So, therefore, if the cos of 2 of omega t was to look something like this, where this represents one cycle, then I am sorry, where this represents one cycle, then minus of cos of 2 of omega t would be an inverted image. So, it would come like this. Here finishes the 1/2 time period starting from t equal to 0, and here it ends with the second time period. So, it is going to be like this, reaching here and coming back here. So this is the way, so t equal to 0. This is the way the inductor is going to, this is the way the inductor is going to function. Now, what happens? Now what happens is, when the inductor's energy is at its peak value and then it let us say starts reducing. So, what is happening? The inductor has to return this energy back to the source, either, or it can also dissipate it in the resistive element. What it means to say is, it now starts returning means, instead of drawing, it starts returning means it starts like acting like a source. Either it returns it back to the supply, or if some impedance or resistance comes in between, it supplies a part of it to it, and it goes back. But this was not the primary function. This was not meant to be the primary function of our of the way we were imagining things to be, and this kind of dissipation degrades efficiency. You will see how, what I mean, I will have more to say on it, how it degrades efficiency. But these unplanned or not designed really, but yet because of the laws of physics they will happen in such a way, activities create a loss of efficiency in supply of power from source to the sink, and we need to later on put some kind of a capacitive compensation a reactive power compensation to balance that. We will come again to that. I am digressing a lot more than what I thought I wanted to. So, I wanted to basically say, coming back to what I was telling you, in time domain this waveform I can write it as this, and I can break it into two components. This component is in phase, this component is in phase, and it always creates a dissipative power, which is the action which was desired, and this component is completely out of phase. This is sign of it is completely out of phase, out of I mean rather at quadrature is a more correct way, not to say completely out of phase, because if you reverse a phase you can probably say that is out of phase. So, this component is actually at quadrature, and therefore, it creates a sin 2 omega t term, which has a average value over a cycle to be equal to 0, and hence does not do any good work. So, that quadrature component will be represented by, let us finish this figure now, that quadrature component will be represented by minus of, you have to reverse the cosine waveform because a minus is there, and set its amplitude to Im of sin of phi. So, this is Im of sin of phi, it goes to 0 here, rises somewhere here to its peak value, its peak value, then come back to 0 and rises, rises to its peak value at this point, comes to 0 here, and again reaches its negative peak at t equal to 0. So, I will rub this so that only voltages and currents are seen here. So, you can now see that this is the IC of t component, and this is the IS of t component, and this is the cosine or component or IC of t component. So, I have got the red as the IS of t and the pink as the IC of t. IS of t and the pink as IC of t, and their difference is the I of t. So, because my voltage waveform is Vm sin of omega t, the reference, this one is in phase and this one is in quadrature, and the to just simplify this expression to show you that nothing changes if I do math slightly different way, I have to take its average value somewhere here. So, let me put this P of t here, and I take average value of, I will just write this because I am going to come to this very soon, minus average value of this is 0, and so it is Vrms Irms cos of phi, unit being watts. So, now you clearly know when I say a quadrature component what I mean. When I say a current component which is in phase with voltage, what I mean to say is that in time domain, this is of course on the geometry, but in time domain this lagging sinusoid by an angle phi has been split into two components such that the one component is in phase with the supply exactly replicating itself, and another component unfortunately has turned out to be in quadrature. It is not unfortunate, it is maths actually, really speaking. So, the other component has turned out to be at quadrature with it. The 90° comes from here, and also it comes from here, that these two angles between these two are 90°, that you see on the time domain graph also, that you see on this. And as I said last time, this VMIM sin phi, this VMIM sin, similar to this component VMIM by 2 or VRMS IRMS cos phi is a component which gives you the average work, while the VRMS IRMS sin phi is a component which we could not use effectively, and this is called as the reactive power. So, this is called also as active power, this is called reactive power, and P plus JQ, which is nothing but VRMS IRMS cos phi plus J sin phi, which is also VRMS IRMS e to the power j phi, is called as the complex power. This is called as complex power, and since the magnitude of e to the power j phi is 1, the magnitude of the complex power is simply VRMS into IRMS, and this S can be written as V e to the power, this is reference phasor, into, this is the current phasor. I should take a complex conjugate of it, and therefore, it can be represented as this is P plus JQ. So, therefore, the complex power, now remember, do not get confused with why did I not just write it as V times of I, why did I write it as V times of I of star. That comes basically from the convention that the power consumed by the inductive element, the lagging element, has to be taken as the reactive power consumed. Consumed is just an English word here. Reactive power consumed actually does not do any active work, to be very honest with you, but you get used to this terminology. And the reactive power which is consumed by an inductive element should be positive. With that convention, this notation of complex power V I star has come out. So, clearly now, let us take a supply, let us say it is feeding a pure capacitor. Okay. So, then if this capacitance is C, then the current which, and this supply is V as a reference, then the current phasor will be I j omega C times of V. So, in the capacitor, the current is going to lead by 90°. So, when I do V I star, I will get 0 minus j omega C V square, because I star is minus j omega C V, V I star will be simply minus j omega C mod of V square, and therefore, you can very clearly see that capacitive, this is units again I said volt amperes, we write as R to show that it is reactive, it is not actually on an average not going to do any work. So, this is the capacitive reactive power is negative. On the other hand, if you had an inductor, if you had an inductor like this, then the phasor relationship would be V equal to j omega L times of I, that is the ratio of the phasors V by I will be equal to j omega L. So, this will be V, then the voltage should be lagging, voltage should be leading the current, the voltage should be leading the current by 90 degrees because of this j operator. So, if I have taken this as a reference, 90 degrees behind, I will draw this as the current, So, when I do V I star, it is V into V by j omega L star, which is V into minus j V by omega L star, which is same as plus j V square by omega L volt amperes reactive. So, now here the inductive reactive power, I can simply say wars, I mean instead of every time saying say, I can simply say wars. Inductive reactive power is positive. So, if you want to compensate, let us say inductive power with a capacitive, then what should you do? You can either put a capacitive element in series, or you can put a inductive element in or you can put a inductive or you can put a capacitive element in parallel. I will give you one example. Let us say this is an inductor of, let us say 1 ohm. Now, directly I am giving you the value in ohms. Okay. So, I will write it as inductive, being inductive reactance, I will write it as j times of 1 ohms, and this is for some reason got connected with a supply. So, what is, let us say the supply is also 1 volt RMS value, again 1 volt RMS value. So, then it will draw a current which is lagging of 1 amperes, and it will be a lagging current, but actually no work will get done. Now, just imagine here a small 0.001 ohm resistance is there. I am deliberately keeping this resistance to be a very small value, so that this approximation that the current is 1 ampere and lagging by current is 1 ampere and lagging by 90 degrees with the voltage phasor is really not disturbed. Even then you can immediately see that I square R or 0.001 times 1 times the current which is RMS value is 1. So, I square R so many watts average loss, average power loss. Afterwards, I will not use even this average word. More, later on it will be clear to you that mostly we will be talking of average quantities only. So, this average power loss means these many joules per second, that this much amount of loss, this much watts of loss will happen per cycle also, will happen in the resistor. Now, let us say this is your home, okay, and this is happening because you are not right now consuming any, you are not really doing any work. So, the parasitic values are causing this. This is, let us say, the transmission line inductance. Now, who will pay for this 0.001 watts? This goes as societal loss, is it not? I mean, you have not your billing. If you look at your billing, it is for the energy which you consumed. Now, you are not consuming any energy, because whatever comes in one quarter is returned in the next quarter, comes in one quarter, returns in the next quarter. So, it is a double frequency oscillation in which net work done is 0. So, your energy meter is going to say that you are not consuming any units. The energy incidentally, the 1 unit is 1 kWh, kilowatt hour, which is 3600 kilowatt seconds, which is same as 3600 joules which is same as I'm sorry, yeah, which is same as 3600 joules. You are consuming 0 joules. You are not going to pay any bill according to your meter, but there is a societal loss, and this resistance could actually be even higher than 0.001. I just took it at that small value just to make my, not to complicate my math, but you could be very much inductive. This resistance could still be something much more larger value, in which case of course the current would reduce, but there would be still I square R which will tend to increase from this value, and this heating loss which is happening in the wires, transmission lines and distribution lines and so on and so forth is a societal loss. Who is going to bear it? You cannot have just like you cannot sow a seed of rupee and get a plant which gives fruits as rupees. So similarly, somebody needs to, you cannot just let it evaporate, you cannot just let this evaporate, because this is supplied by a generating company and the generating company wants the revenue for having supplied this, but the consumer says I have not consumed anything, and the company which is taking care of the transmission and distribution and the wire business and so on and so forth, that company obviously is not, it just a transporter, right? It is just a transporter from source to sink. Why should it pay for this loss? It's in the business of transportation, it's not, so it's also not going to pay for it. So what is done to handle this kind of situation is that distribution companies typically for large loads and I mean enforce that the power factor should be held within a tight band, let us say 0.95 to 1 per 1. Cos phi maximum value is 1, minimum is of course I mean -1 you can say, but actually I would just worry about 0 to 1 range, because if it becomes -1, the sink becomes the source and source becomes the sink, that is just a reversal of the thing. So they want the power factor to be held in a tight band, so that there is no reactive power happening. This loss is only coming just in the, as I am showing you in this example, this loss is happening only because of the reactive power component of the current. There is this is my V, this is my I, it is completely reactive, and this is causing the loss to take place. So what they say is, put a, let us say, put a parallel shunt capacitor of -1 ohm. I mean in this beautiful example, very simplistic beautiful example, let me just put a capacitance of -j1 ohms. Then what is going to happen to I net? I net will be 0. The I net being 0, why is that happening? Because this is the voltage, this is the IL, and equal and opposite is IC. So the energy exchange now is in steady state, the energy exchange just happens between inductor and capacitor, with nothing steady state exchange, with nothing being any further pulled from the supply. So they just play this game of power exchange. They are playing that game, no doubt. Currents are going to flow. This is actually going to draw this particular value of current, and this, because this is also energized to the supply, is indeed going to draw this particular value of current. But because they are in phase opposition, this is actually phase opposition, this is not quadrature. This in fact now, because they are in phase opposition, they tend to cancel, and effectively nothing gets drawn from the source. So obviously this loss of 0.001 watts is not going to happen, and so everything is going to work out fine. Now, since I am on this topic, let us say that this I am drawing 100 volt amperes apparent power, okay, but power factor cos of phi is 0.8 lagging. Lagging means if this is V, the current phasor is now at an angle of cos inverse of 0.8, which is some 36.86 degrees. So, this is the situation that I am having. So, the average power P, now I am only showing it by capital P here, is going to be V I cos phi, but V into I is the apparent power magnitude of the apparent power S cos of phi, which is 80 watts, and the Q is positive in this case because the power factor is lagging. So, if 1.8, then sin phi has to be equal to 0.6 because 0.8 square plus 0.6 square is 1. So, therefore, this Q is going to be equal to 60 volt amperes reactive. Now, this is inductive, by the way, just you know this now. S is in our case 80 plus j times of 60. Now, the question is, I have given you the motivation. This 60 vars is a lot of unnecessary current which is being drawn. So, let us fix up some supply value. Let us say that supply is of 100 volts RMS. Later on I will also stop saying RMS because now onwards I have told you that my phasors will be talked of in terms of RMS, and RMS notation I am going to sort of explain a bit further later on, but right now let us say it is 100 volts RMS. So, if S is V of I, mod of V into mod of I is therefore 100 into mod of I, and my apparent power is S is also 100. So, therefore, the current which it is going to draw is 1 ampere again the RMS value. This is the current which it is going to draw. So, the impedance V by I am just looking at the magnitude of the impedance of the load is equal to 100 by 1, which is same as 100 ohms. Of course, it is a complex impedance. Impedance is a complex quantity, but I am looking just right now at the. So, it is a R plus jx. I am just looking at the magnitude of R plus jx, and it is equal to 100 ohm. So, now let us say wire has 1 ohm resistance. So, 1% of my load value, one wire has 1 ohm resistance. Then, and now this is approximate power loss, this is approximate power loss. You can make your exact calculations, no problem. I am just trying to illustrate to you a small point. So, the current drawn is 1 square into 1 ohm. The current drawn is 1 square into 1 ohm. So, therefore, 1 watt loss happening in 1 watt loss is happening in the wire. you can check it out actually. This Z will be equal to 8 plus J6 ohms. If you just use the fact that the power factor is 0.5, so this Z into e to the power J5 should be the value of the complex number. Then actually Z plus R wire will turn out to be 9 plus J6 of ohms, and this value is a square root of 81 plus 36, so 9, I am sorry, so 7, and square root of 117, square root of 117, square root of 117. So, this is going to be 10.81 ohms. So, approximately this is going to be mod of Z is going to be 10.81 ohms. So, if the current gets impedance gets changed to this value, truly speaking, now the current that it will draw from a 100 volt source, 0.8, so 80 plus J60, 1 watt. No, this goes, this has to be changed. In fact, I was surprised why 10 has gone to 10.8. That is significant change for me. This 1 ohm has become 81 plus J60, and so now this is, let us do the calculation here, 81 square plus 60 square, 81 square plus 60 square, and then let us look at the square root. So, 100.8, 100.8. So, this is mod of Z net is 100.8. Initially without, so the new current that it will draw is 100, instead of 100 by 100, it will actually draw a current which is from the supply that it will draw is 100 by 100.8. So, let us do that, reciprocal of this into 100, that is 0.992. So, it will draw 0.992. So, this is the point. I mean, when I make an approximation amperes, please understand that it has to be a valid approximation. So, 1 ampere becoming 0.992 for illustrating a point, is good enough, you know, it's valid enough thing to do. So, again coming back, I mean, we are digressing and moving and going back and coming further, that is fine. Now, I approximately have a loss of, therefore, 1 watt loss happening in the wire. Now, I don't want to have that loss. So, what should I do? Ideally, I should put 60 watts inductive is my load. Suppose I put 60 watts capacitive shunt compensation. Suppose I put 60 watts capacitive shunt compensation. Then my load was consuming 80 plus J60 minus, so this is my R L, and I put a 60 bars. We can work out the capacitance values later on. I put a 60 bar capacitive compensation here. Then the net load S net will now only become 80 watts. So, therefore, this 80 watts is now being delivered at power factor unity. cos phi is 1, because there is no q part. If there is no q part, then the V I cos phi cos phi is 1, and so this is the I. So, therefore, the current which is being drawn will now reduce from 100 volts 80 watts divided by 100 volts would turn out to be only 0.8 amperes, and so the loss will reduce from 1 watt to 0.64 watts in the wire. So, a 36% reduction in loss. Somebody gives you 36% rate of interest on your investment. Would you be happy or would you not be happy? So, this is a significant amount of loss, and any further reduction in loss is not possible unless you do something about your wire resistance. But this is a good enough loss, and this is the reason why you will always find that with any big load you need to provide a capacitive compensation to reduce the magnitude of the current for the same amount of the active work which is done. I think we will take a break here, and I will continue in the next class. Thank you.